Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lessons, we were talking about Lenz's law and Faraday's law of electromagnetic induction. We said to find the direction of a current that is induced, we'll use Lenz's law, and to find the magnitude of the induced EMF, we'll use Faraday's law of electromagnetic induction. So, by the way, to find the magnitude of the induced EMF and also a current that is induced, to find the magnitude of EMF and current, we'll use Faraday's law of electromagnetic induction. So what did Faraday say? He said that, or he states that the EMF induced in a closed circuit, it is directly proportional to the rate of change of magnetic flux in that circuit. We also learned about a few study tips regarding how to use Faraday's law of electromagnetic induction. One of them was, Gutman, if a coil is pulled out of a magnetic field, remember, pulled out of a magnetic field, that means it was inside a magnetic field, but now it is pulled out, yani there is initial magnetic field or B1, but B2 will be 0 because it is pulled out of a magnetic field. If it is inserted into a magnetic field, that means it was not there, kata B1 is 0, B2 will have a certain value because it is going to be inside the magnetic field. We said in order, or if the radius is given, you can always use or to find the area, you can use pi r squared if we have a circuit, for example, a coil or a circuit loop here. And then to find or, if the dimensions length and width is given, you can find the area by saying length times the width here. And then we also mentioned that if current or resistance either given or required, you can always use Ohm's law, which R it is equal to EMF over the current to find whatever that is unknown here. Basha, now, and then we solved 3 questions, and then we ended up right at this question. So let's begin right at this point right here, Basha. So here's where we're going to go, or we'll start at this point. We have this question. What does it say? By the way, very good question here. It says a rectangular coil of 0.5 by 0.085, Basha. So these are, we can say, the dimensions of a coil, by the way, don't forget. Okay. These are what? These are the dimensions, or you can say the length and the width of a coil. All right. So remember this, we have a rectangular coil. So let's say this is a coil here. The area of a coil, because it is a rectangle, it is going to be length times width. So obviously we have the length and the width. Here it does not mention which one is the length, which one is the width. It doesn't matter as long as, because when it comes to the area, we just multiply them here. So it really doesn't matter which one is the length and which one is the width at this point here. But clearly the longer side would be the length, the other side would be the width here. It says positioned so that the cross-sectional area is perpendicular to the direction of a magnetic field. When it says perpendicular, yani the angle between the magnetic field and the area, or the direction of the area, is 0 degree, which obviously that would give us cosine, that would give us 1, because cosine 0 is 1 of a magnetic field, bablan lira, of a magnetic field. It says the coil has this many turns, that would be 75, and a total of resistance. Good man. Whenever resistance is given or required, don't forget to use Ohm's law, and the field decreases. I want to underline this one here. It says the field decreases at a rate of, whenever in physics, whenever we have something says at a rate of, yani something divided by what? Something divided by the time, we could say. Basha? So at this point here, we can say that something divided by the time here. But what is it exactly divided by the time? It says the field decreases. Isn't that changing here? So the field is changing. That means delta B over delta T, which gives you this. That is 3 Tesla per second. But because it says decreases, you will have to write a negative, Basha. That is what we have. Because in physics, we know that if something increases, that is positive. If it decreases, it is negative. Basha, you might say, Mr. I don't know how, how do I know this is what it means here? Now, you can see that, for example, it is written Tesla over second. That is obviously Tesla for magnetic field, and then Tesla or second would be for the time here. So the question says, what is the magnitude of the induced current in the coil? Basha, you can start writing what is given here. If not, you could just start right away. So here's, I'll be starting with this. We can say, in order to find the area of a coil, that is length times the width here, Gutman 0.085 Basha. We'll consider this as the length here, and then the width is 0.055, and then you just do the math, you can find the area. Gutman, the next thing that we have says the angle is 0. The number of turn n, it is 75 turns. تدي كشمانية and a total resistance قال لي resistance كمان تندا it is 8.7 ohms. The field decreases Gutman at a rate of kata delta B over delta T. The kata سبابة قال له negative AB, it is 3 Tesla per second. Basha. And then now what is the magnitude of the induced current? Kata أو current on these boots and that. Zohar Basha. Starting with this equation here Baba Gutman هر كاتك باسي current يعني resistance كرابو يعني دعوة كرابو كاتي يز ohms law دكاتا سدكاتا EMF Basha lesser current or over current. We want the current, so current دكاتا سدكاتا EMF over the resistance. Once again, current دكاتا resistance come on, it is 8.7 ohms, but we don't have the EMF induced. So now you have to find the EMF induced, and then after that you can plug the number here and then find it here. Basha. So now if I want to find EMF here, man EMF and the bubble and the induced EMF the negative according to Faraday's law of electromagnetic induction, negative NA cosine theta delta B over delta T. Now plug in the numbers, negative N جماري ترنا كان 75 بو باشا area كمان you have to say length times the width which is let's see Gutman 0.085 باشا times 85 times 0.055 Basha times Chibaba. Let's just see if we could do that times negative 3. I got no negative AB because that is the rate of change of the magnetic field. Then because it is decreasing, so we'll say negative 3. So once you find the EMF in here, let's see what is it equal to. EMF later dakata 1.05 volt Basha. Now after you find the EMF, now all you have to do is just bring it back here and then write it down. 1.05 divided by 8 or 8.7 kata. The current that we get it is going to be 0 point something, 0.12 amperes, and this is how you can find the current that is induced through this, you can say, process. Kata, what are the ideas Baba in this question? Of krani kalere dahetia mane kamzar labo to find the area. We're given the dimensions here, length and width because it is a rectangular coil. So we multiply the two to get the area. That is one of the ideas. The second idea says fill decreases, which means negative at a rate of yani. Whenever it says something at a rate of Basha, that means that thing is divided by the time. Kata filled at a rate of on the fill decrease the katan at this rate babbling later rate that is 3 Tesla per second. But the decreases kata, I will just say negative 3 Tesla per second. Again, now got man tamashayin take about Tesla per second. That means delta B because it is changing obviously. So this is delta B over delta T, which is given directly here. Basha. Now all you have to do, good man, that's the baba. In order to find the current, we need the EMF, even though lo persare pena got EMF okay babino, but hata current babino. You'll need the EMF, so you go find the EMF first and then come back and then you can find the current. Basha kata persara ka asana baba bas tibga inshallah hitsi pena zor basha persara shmane zor asana. I think you could do you could solve this question yourself then just plug in the numbers and use the equation baba. I would love to solve this question for you or this question too Basha. So what do we have in this question? The question says a student attempts, watch this, Basha. So we have a student who's attempting, we're trying to make a simple generator, Basha. Make a simple generator. That is what he's trying to do. All right. It says to make a simple generator by passing what? By passing a single loop. So single loop, that means N. That'll be the number of turns is just one here, of wire between the poles of a horseshoe magnet, that is a type of magnet, with a this much field, Basha. So this much field Tesla, that'll be the unit of magnetic field strength. The area of the loop is this much, area is given, that is also. All right, this by the way says, and is moved perpendicular to a magnetic field. When it says perpendicular, the angle between the direction of a magnetic field, then the direction of the area is 0 or parallel to one another. And قال لي بينهم صفر بابا. Question could delay in what time interval? So delta t, it is unknown, Basha. Will the student have to move, Basha, the loop out of a magnetic field? Because if I move out of the magnetic field, yani B2 will be 0. Now we can call this one B1, Basha, in order to induce an EMF of 1.5 volt in here. So this is the EMF that is induced, which is 1.5. Kata, if we want to write the equation here, Baba, Gutman, we could write the given information too if you want to. Gutman, N is 1 turn here. I got Lebi. Tzidi Kashmane Gutman, the magnetic field or B1, it is equal to 2.5 times 10 to the power negative 2 Tesla. And B2, because it is moved out, 0. Basha, Tzidi Kashmane area which is 7.54 times 10 to the power negative 3 meters squared. And then the question, by the way, says the time is unknown, so find the time. And then in order to induce an EMF of 1.5 volt. So of course, based on the information given, we can find the time using Faraday's law of electromagnetic induction. EMF دكاتة سليرة EMF دكاتة negative n a cosine theta, because the magnetic field is changing. So we can say B2 minus B1 over delta t. The question says find delta t here. We could use this, but if you're ever going to use this, make sure that you use a bracket here. And then you could just swap the delta t with the EMF here. So now we can say delta t the negative n. By the way, B2 is 0, so you could just ignore that or write 0 instead. Negative n a cosine theta. So 0 minus this, that will become negative B1, by the way, right? And then divided by EMF. O negative baba, the beta positive. Kata delta t later the kata. What is that equal to? It is 1 times the area, which is 7.5 times 10 to the power 7.54 times 10 to the power negative 3 times cosine 0 times negative the beta positive B1. What is the magnetic field? That is 2.5 times 10 to the power negative 2 Tesla, all right, divided by the EMF induced, which is going to be 1.5 volt. Now, once you find the time, right, this time here, it is equal to 1.3 times 10, or 1.3 times 10 to the power negative 4 or 3. I think it is negative 4. We'll double check the answer now. Negative 4 second here. Pasha? Now, let's double check. The time that we get it is 1.3 yes times 10 to the power negative 4 second. Now, I would like to talk about this number a little here. Now, I need you to know that in order for the student, Basha, to induce an EMF that is 1.5 volt, he has to pull the coil out of the magnetic field in a time that is equal to, if we write this one as a normal number, you can say 0.00013 seconds here. See how short the time is? By the way, human or average human reaction time, it is about 0.2 second. Masha, you need 0.2 second, like to react to something. That is called, like a reaction time. For some people, you can call it the reflexive or whatever. All right. So this is how much time it needs or it takes you, for example, to start reacting to something or whatever it is, Basha. But this is the time that we get. This is how fast the student is supposed to pull the coil out of a magnetic field in order just to induce 1.5 volts. So do you think the student will be able to do this? Because part of the question says, is this a practical generator? Well, the answer is no. Why? Because mainly you can see that this time is very, very short. The student will not be able to pull the coil out of a magnetic field at this short time here. So it's impossible to do that. Since it is impossible, so this generator, it is not a practical generator. It's not something that is very useful, Basha. This is what it means. Is this a practical generator? You cannot pull the coil out of the magnetic field this quick. The voltage that this generator induces, that's not that much. It's just 1.5 volt. You cannot use it that much. And then another reason why it is not practical, this coil has only a single babbling coil. Oh, أنا بابا هيز مشكلة جنية. I guess single coil تشيبي أنا voltaic برهم داني and generate the for small. But the main issue is the student cannot pull the coil out of the magnetic field at this speed. And we can say this is the primary reason why this is, or this generator, it is not a practical generator. Asha? That was regarding this question here. Also, I would love to solve this question for you too. Let's say a coil of 325 turns. جيربو زور باشا اسمعني بابا بلا coil كمان هي with a 325 number of turn كاتا and جماعة turn كان 325 turns باشا and an area, here's the area, area كمان سنة بابا, it is 19.5 times 10 to the power negative 4 meters squared. It says removed is removed from a uniform magnetic field. How can I go to removed from magnetic field? يعني B2 ده بيتا سن بابا ده بيتا 0. An angle, قاعد لي بي angle لكي تسن or theta, it is 45 degrees. At this point you cannot ignore the angle or write 0 instead. You have to write 45 in a time كمان سنة, it is 1.25 seconds. باشا بشارة كده if the induced EMF باشا it is 15 millivolt. قاعد لو ملي بي 15 milli بابا. How much is milli? 10 to the power negative 3 volt. باشا it says what is the magnetic field strength. فقر بيتوكا صفر اللي بابا كاتا B1. What was the strength of a magnetic field that the coil was inside here. باشا يعني بكردك B1 سنبوا. زور باشا. At this point here بابا we could just do this one. EMF دكات it's a negative NA باشا cosine, because the magnetic field is changing, cosine, we can say B2 minus B1 over delta T here باشا. And because we said it is pulled out of a magnetic field, kata B2 is 0, you could just remove this right away at this point here. Now what is left is basically we can say negative B1 over delta T here. But at this point here, we want to find this right here. Kata, you could use cross multiplication. B1 the kata sababa. And by the way, this negative and negative cancels out now. So we can say B1 the kata EMF times delta T divided by number of turn, cross-sectional area, and cosine of the angle. Now, once you do the math, you can get the answer. EMF كمان سندا قد ما 15 milli negative 3 times time كت سندا 1.25 seconds divided by number of turn كان قد ما سندا. The number of turn is 325 times the cross-sectional area, that is 19.5 times 10 to the power negative 2 times قد ما cosine goshake, and that is cosine 45 degrees here. So multiply by cosine 45 degrees. Now, once you do the math, of course, you can find the magnetic field strength, and you can call that B1 if you want to, which is about 0.042 Tesla. And sometimes you might be, because this number is small, you might be given this in milli. You can move this one 3, because milli is negative 3, so 1, 2, 3. That'd be what? That'd be 42, or you can say it is equal to 42 milli Tesla. So this is the magnetic field. We can say magnetic field strength. Basha. It was, the coil was in bubbling before it got removed. Yeah, before it was removed out of the coil. This is how you can do that. Later, bubbling, they change in the magnetic field. Mandito baba agalibi basha. After you find this one, this is 0, so you could just find B1, which is pretty much the same method. But it saves you 1 or 2 steps. That'd be the best. Bashkaka. And now let's move on to another concept, which is self-induction. What is exactly self-induction? I want you to think about the title of this for a second. Self-induction. So there is an induction within the coil itself. This is why, or the reason why we call that self-induction. And we have a pretty, we can say easy definition for that. That also helps you to understand this as well. So self-induction is the creation of the induced EMF, Basha, the creation of bubbling of an induced EMF, but inside a circuit. But why is that? as the result يعني بابلن due to the result of changing يعني varying its own current. يعني كاتك كويل اكتبوا بابا currenti أو كويلي when the current of this coil itself is changing, then an EMF will be induced inside that coil itself. Oh, and let me perhaps maybe give you an idea of what we're saying, and then do better, and then or perhaps maybe later we'll get back to this one. So we have a battery, a power supply, a switch, a rheostat, or you can call that a variable resistor, where that allows you to control the current of a circuit. And then from that it goes to two coils, right? Two coils, and then from these two coils it goes to you can say an ammeter here. We could just bring this one here, and then from this it goes back to this here. So now regarding this one here, there is a coil. That is one. And this is the other coil here. And there is, we can say, an iron core here. So there is connected here. From this it goes to this one here. And then from this one, you can see that it goes to the ammeter or the galvanometer here. So now, what exactly happens, Baba? Once you connect the circuit, the magnetic field, or you can say a current, will flow through the circuit, right? That is one thing you need to know. At any point, if the magnetic flux of a circuit change, clearly that would lead to an induction, lead to the creation of an EMF inside the coil itself, and that is what is called self-induction. So how can we do that? You could do that by, like multiple methods or ways here. One of them is by doing this, for example. So now once you close the circuit, let's say, a current will be flowing through the circuit. Basha will set the current that is passing through the circuit. Let's say we'll use a current of about 50 milliampere. This is just an example, Baba. It could be any other currents, it doesn't matter, Basha. The reason why we're using a small amount of current, because we're using a galvanometer as an ammeter. So we'll use a small amount so that it can still read it. You'll have to use a normal or an ordinary ammeter. So what exactly happens? Now, there's current flowing through the circuit, so there is a magnetic field around the coils here as well. So, but now at this point here, for example, there is a magnetic field. Watch this is what the book says. It says if the coil is connected, or this iron core, by the way, it is, so at this point here, there are two things you need to know about Baba. So the book says the coil is connected, so there's one thing or two things actually you could do that. So either this coil was not connected by a wire. Now you can connect that, because the moment that you connect the coil with a wire, current starts to flow through the circuit or the coil. I get current, for example, as soon as current starts to flow through the coil, now then there will be a magnetic field around this. So we can say the magnetic field starts to increase, and that of course causes a change in flux, right? So this is one thing that we can do. There's another thing that you could do actually. These two coils possibly could be connected, but now if we add this iron core here, right, that also changes in the magnetic flux. Why is that, Baba? That is because this iron core transfers the magnetic field of this coil, right, also to the other coil as well. So we can see that lead to a bigger magnetic field in here. So by doing any of the two here, it would be best to say when the coils are connected, now you connect the wire to the coil, the magnetic field around the coil start to grow, and that leads to a change in flux, Baba. This flux or change in flux leads to a current to be induced, Basha. This current that is induced, it will have its own magnetic field, just like we said it before, when a magnetic field will be induced. This magnetic field will oppose the magnetic field of the coil, Bablin. So because like these two will be in opposite direction. Magnetic field, the coil start to grow. So how do you keep the total the same? By being in opposite, by opposing that one. But man, that current that is induced, by the way, don't forget there is a current that is flowing through the coil already. They can call that current through the coil, Basha. But man, this current that is induced will also, that is going to be opposite, Basha, to the current that is on the coil. Why is that? So that it's going to be opposite to reduce bubbling or to keep the total magnetic field the same. So what happened, or what do you think will happen as a result of this? Agar tamasha meter ke baba, this ammeter here, this is an ammeter. It reads the current bubbling of the circuit, Basha. And you can say the total current of a circuit here that is flowing through the circuit. You will see that this ammeter is going to read less current, Basha. Less current. And why do you think it is going to read less, Baba Gutman? Because these two currents, the one that is induced and the one that is flowing through the coil, will be opposite to one another. Basha Gutman, we induce bo Basha will be opposite to the one that is flowing through the coil. And as a result, Gutman, current circuit kam debito barba basaga lebi baba. Gutman, this current decreases only for a fraction of a second. Yan as long as there is a change in a magnetic flux, Basha, hata kam nabito, Basha, it only decreases when there is a change in flux, but this flux is increasing, right? So this is what happens here. So what exactly happens if, let's say, we remove the coil, or let's just say remove the coil, Basha. So if you remove the coil, that is the same effect as moving a magnet away from a coil, Basha. But now the current on the, or the magnetic flux, or the magnetic field around the coil, that is going to decrease. If you remove, Basha, if you remove the coil, yan bubbling, if the coil is removed, what do you think will happen this time, Basha? Gutman, the magnetic field this time, right, it is going to decrease, which means that there is a change in a magnetic flux. Gutman, as long as, or anytime there is a change in magnetic flux, that induces a current in a circuit. Of course, an EMF and a current too here. That current, of course, this will have its own magnetic field. Gutman, it induces an EMF, Basha, and let's say induce an EMF here as well, right? This what happens, Gutman. This current here now will have its own magnetic field, but now this magnetic field that is going to oppose the magnetic field of the coil, which is decreasing or receding now. But how does it, this magnetic field is decreasing, so how do you think this will oppose that? By being in the same direction as the magnetic field of the coil, so that it can kind of like back it up, magnetic field, or in order to keep the total magnetic field the same. But how can it be the same direction, Baba? Current induced to be this time here, it is going to be the same direction, Basha, as the current, that is passing yan bubbling on the coil, flowing through the coil. So we can see that based on this. If you look at the ammeter here, the ammeter now, it is going to read more current, Basha, or it is going to read higher current. Why is that? That is because, Gutman, these two current now, it is going to be the same direction. What's the same direction, Baba? Gutman, square magnetic field, coil yan bubbling coil is decreasing. So how do you keep it, prevent it from decreasing? The current induced has to be in the same direction now as the current that is on the coil, so that the total magnetic field stays the same. Gutman, هر كاتك نتواني تنها اون دي بزاني بابا اگر magnetic field يسر كويلة كان زيادة كرت او كاتي بابلين كرنتك درز دبي EMF كرنتك of course. This Gutman current will be opposing and opposite to the current that is flowing through the circuit. حتى magnetic field لكي بكونستانتي بهاليتو. باشا اگر for example the magnetic field is decreasing او جارة دوبارة same thing happens. Gutman EMF كرنتك درز دبي, but this time this current that is inducing, of course, is going to be in the same direction as the current that is in the coil to keep the total magnetic field the same. Basha, as the of course you could do that. The same thing happens the moment you turn the switch on. For example, the moment that you turn the switch on, currents start to flow through the coil, magnetic field the EMF that is induced in the coil will be opposite to this one, so that to keep the total the same, the current we can increase or decrease the current that is through the coil, so we can have we can achieve the same result. Basha? Katalira we getting baba that one blim oh note akhiri laharham we getting to what exactly this note is about. Then Habzan Baba Gutman the Salfian bubble and EMF will be in opposite direction when the current is increasing, Basha, and will be in the same direction when the current in the circuit it is decreasing. Now let me walk you through this one more time. Gutman self-induction, it is the creation, the production, the producing, inducing Baba of an induced EMF in a circuit due to what? Due to the variation of its own current. Basha? Yani Kateka current that leads to an EMF to be induced. That EMF induced, you can call that self-induction because it is inside itself. So how do we do this one? Like if I walk you through these steps real quick, it says the circuit in a figure 6.7 is made up of a galvanometer, which is used as an ammeter here. An electromagnet, you could say that made of two coils, which you can see there, right? Each of 1,200 turns, and a rheostat, which is a variable resistor, and a suitable power supply, just like a battery, for example. It could be any other power supply that can provide enough current to be flown in the circuit. We'll move the rheostat until the ammeter points to 50 milliampere, for example. It could be any other value, that is totally fine. Then when the coil is connected, Baba, okay, what will happen exactly? The current decreases. But here it does not, the book does not explain why the current decreases when we connect the coil. Basha, remember Baba, coil can connect the can magnetic field coil can it increases when it starts to grow. That of course causes a change in flux. When this happens, EMF current will be induced. Current induced Baba will be in opposite, and in the direction of current induced will be opposite to the current that is flowing through the circuit. As a result of that, the current of a circuit decreases, but that is only temporary. Basha, that one blend. Basha chikati agar flux and magnetic field katsidi kana gore au kati EMF induced nabian there's nothing, so the galvanometer needle, the ammeter now it can read just fine, like it will read a constant value. Basha, when the coil is removed, Baba, the current increases. But exactly what causes or what makes the current increase when the coil is removed? Baba, once again, so once we remove the coil, that magnetic field it is decreasing when so there is a change in flux again when so how do you keep let's say the magnetic field or prevent the magnetic field from decreasing? Induce the bibablin will be in the same direction as the current through the coil magnetic field this is why Gutman is now they are both in the same direction. As a result, Gutman the ammeter read a higher number and Bablin reads more, even though says the coil is removed. Basha. The current increases low. Labarse Gutman induce they will be in the same direction. So as in total result so, but Agali Gutman magnetic flux can decrease because it is bubbling, the coil is removed. Now, when the intensity of the current increased or decreased, Basha, in a circuit, bubbling in a circuit, the magnetic flux crossing the number of turns will vary, change the B, and of course that leads to a self or back EMF to be created, which is Basha, when the current is increased, Basha, what will happen here? Gutman back or opposite. Gutman kateka karenteka ziyadaka or karente induced the bibaba. It is opposite yan bablin. So this is the reason why we call it back EMF. It's almost like backward, opposite to that, Basha, and it is proportional EMF, Basha, when the current decreases here. Gutman agar karenteka decrease kat now zare EMF and bablin karenteka will be, both of them will be in the same direction as we could say will be the same direction as the current that is in the circuit, so this two will be added. This is why we say it is proportional. Yani is going to be added to the total because they will have the same direction, then the resultant will increase. Basha Gutman Tili Dibaba proportional kata back EMF legal circuit is going to be in the same direction. But so let's حالة when the current of the circuit is decreasing. When the current, we can deduce the following. Basha, if a magnetic flux through a coil is varied, يعني change due to a variation of the current in the coil, current يصير coil كان جورا بابا magnetic field كده جورا that leads to the change of magnetic flux. Okay, this variation affect the coil and leads to an EMF that resists the variation of the original current. باشا قطمان هر جوران كاريك لو كويلا لكرنتي وكويلا أنا نروف دا بابا أو ودا كإمف أكو كرنتك درس بي these EMF and current here قطمان always tries to resist the variation, tries to resist the changes that are here. قطمان أجر كرنتك زياد كا the current induced will be opposite. Basha, to keep it the same. Agar kam katan is going to be the same way to prevent the changes one, yeah, to keep the total the same. Agar lo khala nabi khrabniya. This phenomena is called self-induction. The 20 or no tashbab the 20 bilis samaraisi ushtana the ka kabas market. Basha, one of the point that we have got man agar current takab gore Basha in a coil or in a circuit got man flux kada gore that induces shebaba induces an EMF. Basha agar liribi got man when the current is increased or when the coil is connected. It's got a magnetic field that is زيادة كبابا. باشا أو كاته أجر current يصير coil كي increase كا magnetic field كا باشا the magnetic field it grows more باشا يعني when the coil is connected that also leads to like a change in a flux bubble in flux كا زيادة كا باشا whether the current increases and the coil is connected that obviously affects the flux and fluxaka زيادة ببابا لو حالتك fluxaka زيادة وتسيدا بيتن أواني قلت man the current that is induced will be in a direction such that to make this flux keep it constant لو يدت واني بلين أو EMF درزبا it is going to be opposite to the applied ما بس لان applied the one that is on the coil بابا قلت man أو current is going to be opposite باشا the current the بابلين this current that is induced will be opposite to the current that is on the coil. So as a result, we can say the current of the circuit decreases here. When we change the current but decrease the current, you can say that the flux would decrease also. That leads to an EMF to be induced. Now let's حالتك this would happen when the current decreases أو كاتي magnetic flux decrease or when the coil is removed عنا شدو بارا magnetic flux أو زارا decrease the below do حالتنا magnetic flux كان decrease the بنبابا اگر current decrease كا يعني coil كا remove بكرتنا أو كاتي قلت مان أو EMF current كا decrease the they will be in the same direction as the applied كما بس لان applied كي بابا the one that is on the coil here. Coil, Basha, and the current that is on the coil, they will both be in the same direction. Kata is that currenti total of the circuit that is going to increase. But changeana baba, it happens as long as the flux is changing, which normally, Gutman, this change happens in a we can say in a matter of let's say second or maybe a fraction of a second. Basha, Kata goran kariana katalina meteraka. That's only like a fraction of a second. Maybe it is just a deflection. Goes back to, for example, to measure what it is because this change, it is only temporarily. Unless you keep changing that, for example, constantly, which is something we normally don't do here. Self-induction is going to be opposite. Opposite to what? In opposite direction. It is going to be the same direction agar currentaka kam bakatan. In order to calculate the self EMF, we assume the following baba. Basha, gutman ista gutman self induction Basha EMF agduriz the but how much will it be induced? Gutman hakatak current bugore magnetic flux kada gore EMF ku current agduriz the but how much exactly will it be induced? We could of course now use an equation to see how much will be induced here. But in order to do that, we'll have to assume the following. The first thing that we have to assume, Baba, it is this. We'll say if a current I traverses a coil, Gutman, agar current bana coil of course there will be a magnetic flux which crosses each turn bubbling of the coil, which is directly proportional to the intensity of a current. Hata current be magnetic flux be basha. If the current varies, magnetic flux because they are directly proportional, basha. But that leads to an EMF to be induced. So how exactly are we going to do this, Baba? We're going to, prove something, Basha, to find how much will it be induced. You're not required to know this, Baba, but of course, knowing this would be a good thing, like it doesn't harm. Basha, good man. The magnetic flux that is directly proportional to the current. When you attack current, be magnetic flux, but for example, if like if we divide both side by delta t here, good man, I get current Baba over some time, magnetic flux at the same time. When you, good man, because these two are directly proportional. I get current if it changed for 2 seconds, got the magnetic flux change for 2 seconds too. And yeah, so if that is the case, we can say that these two will change. Basha, I get on a change, now I get current change, then the magnetic flux will change as well here. Zor Bash, but later Baba, it's man here, our relation, I get money relation, we can equation, we'll have to add a constant to this. So we can say, what is it called here? We can say change in flux, Baba, over time. It is equal to, with my later, agar لزياتي يتبدل agar relation became equal أو كاتي دي be constant تشيلو زيات can, which in this case, of course, we could just say a constant here. Basha, times change in current over the delta t. Basha, now we can multiply both sides by negative n. Basha kaka, by what? By negative n. What will happen exactly? Negative n, change in flux over the time. There the negative n times a constant. Basha, constant times delta I over delta t. Now, O n times constant, n times constant. Oh, the beta constant and you can call that what? You can call that L, which is called the coefficient of self-inductance. Bashbaba, instead of n times constant, we could just write negative or just L here. With my negative, change in flux over delta t, we can write negative instead of this two together, Baba. We'll just write L, which we said that L stands for the coefficient of self-inductance times change in current over delta time. But we've learned that, huh? Does this equation remind you of anything, Gutman? Change in flux over time n times that. Isn't that Faraday's law of electromagnetic induction with a -2, by the way? So we can say Faraday's law, or according to Faraday's law of electromagnetic induction, this two together, Basha, it is equal to the EMF that is induced, by the way, which is equal to -L delta I over delta t. If you want to make, for example, now this is an equation you need to know, Basha. EMF induced -L times delta, or the rate of change of current. Basha. And if you want to make L the subject here, we can say L the negative EMF over change in current, or the rate of change in current in here. According to this, Baba, we can see that. So coefficient of self-induction later the kata EMF, Basha, the EMF that is induced, obviously the kata over the rate of change of current here. What exactly, Gutman? L stands for the coefficient of self-induction. Coefficient of self-induction or self-inductance. Coefficient of self-induction, inductance, which is also measured in what? Measured in Henry. We can say measured, or the unit of that, measured in Henry. Basha, and the symbol that we use for Henry, it is H. Basha, this is what we have. We know that, for example, at any point if the current change in a coil, that leads to a change in the flux. If the flux is changing, that means there will be an EMF that is induced. That EMF, you can call that back EMF, or the EMF induced. As long as, or like at any point if the current is changing, then there will be an EMF that is induced. This EMF and the current that is induced will be opposite. The EMF and the current that is induced will be in the same direction, Basha. At this point, Baba, you can see what is Henry equivalent to, by the way, this equation here. Let me start at this point, as a matter of fact. Gutman EMF, it is measured in volt. This is Henry, we can say, and this is, we can say, current, which is measured in ampere, we can say. So you can just say Henry times ampere divided by say divided by the second baba. Kata volt dekata say Henry times ampere over second. But if we want to make, for example, L the subject or Henry the subject, man Henry, what is it equal to? It is equal to volt over ampere over second here. Second the tita seri baba, we can say Henry dekata volt second over ampere, and this one been وزاري as well. I got له خالة نبي بابا. And there's one more thing, by the way. قلت مشاعر بكي بابا. We were using Ohm's law اللي بيرد بوبي. But on Ohm's law the cat is V over ampere. يعني EMF over ampere in here. But this is resistance, which is measured in ohm. Basha, this is voltage and this is in ampere here. That's right, current here. Instead of this one, you can see that at this point here, instead of writing volt over ampere, I could just say Henry. It is equal to ohm second. When you with a 20 blade the kata ohm over hertz as well, because you know that if you move this one here, that'd be 1 over second, and instead of 1 over second, you could just write hertz as well. Basha baba kata. This is this been in Wizari. Basha kata Henry. It is equivalent to what? To ohm second. Nagatan. All right. These are the equation. You don't have to know like how or where did it come from, as long as you know these two equations. That'll be enough. EMF that's a negative L. What does this negative kaka represents? This is stated by Lenz's law. EMF and these will always be in a direction such that it opposes the change that made it. That is what we have. L times delta I over delta T. And you make that the subject. This is what it becomes, and that's it. Yeah, later, Henry and some of it is equivalent unit. Later, the definition of coefficient of self-inductance L, which is a ratio of the magnetic flux that crosses a circuit to the current that traverses this one here. Now, you could turn this definition into an equation here. We can say L the ratio and it's any division divided something magnetic flux that would be flux. It doesn't say it's a change in a flux, magnetic flux alone to what? To the current that traverses this one, or just divided by the current here. So that would be, Basha, that would be the equation for magnetic, the coefficient of self-induction. And of course, later you'll see that the next page, there is a constant here as well. So we can say N flux over the current, Basha, that will be the coefficient of self-inductance L. Which is good man, this is number of turn, which is a constant, so we normally don't say that, but that is what it is, the equation for coefficient of self-induction, or you can say inductance or another equation for that, Basha. So whichever you have. All right, I believe we'll do one more thing, Basha, and then we'll end this session. Hopefully it's not going to be too long. Yeah, we'll talk about the self-induction of a solenoid. So what exactly self-induction of a solenoid is, I need you to be aware of this one here. It says a solenoid, as shown below, is connected across a battery. The moment, for example, the solenoid has N turns and a length of L and a cross-sectional area of A here. What happens when you close the switch? Now current starts to grow from 0 to a certain value. The moment you turn the switch on, the current starts to flow through the circuit. Zero. So that is going to have a certain value. Magnetic flux that also increases. Previously, before we turned the switch on, magnetic flux was 0 because there was no current. But now after the current flows, there will be a certain magnetic flux as well. To a final value. Magnetic flux also increased from 0 to a final value. So that, of course, leads to an induced EMF, which is going to be opposite to the original one. How exactly are we going to start or to begin with this one, Baba? Now, remember this, Basha. Now, we have two things here. We've learned that, Gutman, according to Faraday's law, EMF the negative N, Basha, change in flux over delta T. What about according, for example, let's say to the equation of self-induction, Gutman, EMF the negative L, change in current over what? Over delta T. These are both the same EMF. If these two are the same, we can say these two parts are also the same as well. So now you can equalize them. So we can say negative N, change in flux, right, over delta T, the negative L, change in current over delta T. Once again, you don't have to know the proving of this. Notice that negative and negative cancel out, so you could just remove them here. Basha, and then delta T cancel out. You can remove this one too. But flux and current baba. These are both increase and decrease together. When you malera current the beta I2 or delta current here, the beta I2 minus I1 when you fluxi duam minus fluxi account. Gutman. The first current, the initial current was 0 because there was no current. The flux is also 0 as well. So what is left now? We can say number of turn times the flux, it is equal to coefficient of self inductance, Basha, times the current here, Basha. Instead of writing flux 2 and current 2, we'll just say a certain value and that's it. So according to this equation here, if I want to make L the subject, then L the and flux, let's say current baba. And this, once we define the coefficient of self-inductance, we defined according to this equation the ratio of flux to the current here. Basha, we actually later so gringa the 20 billion Henry later, because the unit of coefficient of self-inductance the Henry and the later baba gutman n number term has no unit, later flux the Weber lesser ampere, and this one also been if I'm not mistaken. Now, if we continue with this baba, right, because we're trying to find the coefficient of self-inductance for a solenoid, I hope you noticed the title. L and flux over the current here. What is the magnetic or the what is it called? What is the flux equal to? Basha? What is the flux equal to? We know that. We've learned that flux AB cosine theta. And if it is maximum, we don't have to write the cosine here at this point. Basha. So this is the area we can say of a solenoid here. What about this one here? This would be the magnetic field strength for a solenoid. And you've learned that magnetic field strength for a solenoid, the mu naught and I lesser L, right? So that is one thing you need to know here for solenoid. Don't forget. We can write that one here. So we can say magnetic flux, the A times, Basha, A times mu naught N I over Ch over the length. Now all you have to do is just bring this one back into this equation right here. So now we can say N times, Basha, flux the A times mu naught times N times the current divided by Ch divided by the current again. Now you can see that we have N and N, that would be N squared, and then there is current and current will cancel out. So what is left, or what will be left in the equation? We can say coefficient of self-inductance for a solenoid, don't forget. Basha, for a solenoid, the mu naught N squared times the area, we could say divided by T. Oh, I forgot the length, huh? Okay, there's the length there. This length just goes down. We could say divide by the length of the solenoid. According to this equation, Baba, you can see that the coefficient of self-inductance for a solenoid depends on mu naught, coefficient of coefficient of magnetic permeability, number of turns squared, cross-sectional area of the solenoid, and also the length of a solenoid. And if you noticed, hopefully you've noticed by now, all of these are, you can say, these are geometrical properties, of physical properties of the solenoid here. This magnetic permeability, how much, for example, for example, the surrounding of the solenoid permits the magnetic field. This is the number of turn of the solenoid. This is the area of a solenoid. This is the length of a solenoid. Whether the current, let's say, is changing in a solenoid or not, the coefficient of self-induction but does not depend on any of those. What do you think will happen to the coefficient of self-induction for a solenoid? It doesn't happen, it doesn't change at all, because it doesn't change or stays constant. But this is the coefficient of self-induction for a solenoid. What if the question says, what is the coefficient of self-induction for a coil? Of course, magnetic field equally and B coily mu naught N times I divided by 2R. So instead of the length, you'll just write 2R here. So what is the coefficient of self-induction for a coil, Baba? We can write same equation, but we'll just, instead of L, we'll use 2R, Basha. It's going to be mu naught N squared times A divided by Ch divided by 2r. Basha? So now this is what it becomes. Yani we only replace the L with 2r because that would be the coefficient of self-induction for a coil. If I ask you a question, what does the coefficient of self-induction or inductance of a solenoid depends on? Depends on 4 factors. Depends on the magnetic permeability, number of turn, was squared Agad-Libby. These are directly proportional. The cross-sectional area of the solenoid, and inversely with the length of the solenoid. And we also know that because this is squared cut that has the maximum effect on the other factors. If we double the cross-sectional area, or like which one has a bigger effect, doubling the cross-sectional area or doubling the number of turn? Clearly doubling the number of turn because that is squared. If you double that, it increases by 4 times, but this one, if you double that, it just doubles and that's it. These are very, very important. Inshallah, we'll try to solve that next time, inshallah. These are the equation. تناوي equation بزانا عشان لقلو equation وانا ديكا اشتا تشيوانيا زور ضرور نينا قلت ما نباسي بسارش معنا كد what does the coefficient of self-induction or inductance of a solenoid Agad-Libby depends on equation كي بنسو and these are what it depends on بس Agad-Libby بزانا تشي direct تشي inversa and square كشتا Agad-Libby باسي بسارة ما كتازا لو زاري عتيتو the life the intensity of the electrical current in a coil change at a rate of onda. The magnetic flux change at a rate of onda. This leads to a creation of self EMF. Then the coefficient of self-induction basha in the coil basha of تسيلي دي لو حالتي بابا but man coefficient self-inductancy coiliad. So this one says coil, does not even says the solenoid, but whether for the solenoid or coil baba doesn't matter. Good man mu naught n squared a. Let's say if it is solenoid that would be L like a coil bu أو كاتي دبيتا تسبابا e coili good man L e coili debita عين shit mu naught n squared times a divided by 2r here. Basha later whether the flux is changing or not, whether the current is changing or not. Basha hits current to flux the equation كده here. نخير kata does not affect this. Kata this one does not change or stays the same. Each one of these are the same thing here. Kata increase no, becomes 0 no, decrease no. Kata it does not change because there's no current or flux in the equation here. Kata doesn't affect. Basha, let this be the end for this session. Inshallah next time we'll talk a little about some of these units and then we'll solve the question that is related to this concept we've just studied. Till then, keep practicing and I'll see you soon inshallah. Assalamu alaikum wa rahmatullah.